Hey, everybody. It's Thursday, November 12th. And as you can see here in the aim today, our focus for this video is going to be all about friction. Now, we're going to do this in a sort of weird way because, like, number one, you've already taken a physics class before where we talked about friction. And so it's not like you're coming into this totally blind. And number two, we've already talked a lot about forces so far this year in this course. So I think from what you know, you'll actually be able to put a lot of this together on your own. And so what I'm going to do here in this video is really just kind of pose questions and sort of give you things to think about in the hopes that you'll actually be able to put a lot of this together yourself. And so what I'm going to end up showing on a lot of these slides here are questions, which will always be in bold. I do not want you to write those down. I only want you to write down the answers, which will come underneath those questions and will not be in bold. And so you're going to see a lot of them in this video, and I just don't want you to waste your time writing down questions because what you need to know are the answers. Additionally, what we should also just say before we begin is that this is going to be a fairly long discussion, and the discussion of friction, because there's a lot that we have to cover. The first thing we're going to do is we're just going to talk about friction in general. The second thing we're going to do is we're going to look at some problems that we've never seen before that happen to involve friction. And then we're actually going to double back and take a look at a bunch of problems that we've already done and involve friction in those problems. So like the Atwood's machine, the tabletop Atwood's machine, stuff like that, we're going to sort of add friction into the mix to see how it works. Okay, so to start us off, let's ask a question. Again, here, this question is in bold. Do not want you to write it down. The question is, why are Newton's laws so counterintuitive to our everyday experience? It's an interesting question. Why are Newton's laws so counterintuitive to our everyday experience? Well, there's pretty good reason. If you think about it, what Newton's laws say are that objects continue in their state of motion. And Newton's laws are counterintuitive to our everyday experience because objects that we see do not continue in their state of motion, but in fact, they slow down. Now, this is a thing that I want to really make sure that everybody gets, because in like the popular imagination, almost everybody gets Newton's first law wrong. Like you hear it in all those like arthritis commercials. If you're ever watching sporting events, they're like, a body in motion stays in motion. Make sure you buy this medicine to keep your bones right? It's true that an object in motion stays in motion and an object at rest stays at rest. But that's only true in the absence of an external force. And almost all tellings of Newton's first law leave off that last part, which is the most important part. Objects in motion tend to stay in motion, and objects at rest tend to stay at rest only in the absence of external forces. And that's why Newton's laws are counterintuitive to us, because we often leave off that in the absence of external force business. And it just seems really weird to us to say that essentially the exception to the rule is actually every single thing that we see every single day of our lives, right? That's Newton's genius. You could easily forgive somebody for saying the law of motion is all objects in motion eventually come to a stop, right? And so Newton's genius comes in saying, no, it's actually not that every object in motion tends to come to a stop. It's that every object that's in motion just keeps on going. It's just that whenever we see moving objects, something is making them stop. And that's an interesting point. And so, of course, now we have to ask the question, well, why do they stop? Why do normal everyday objects not continue in their state of motion, like as a block slides along a table? So take like your calculator or something and just push it on the table like I am right now. It eventually comes to a stop. Why? Well, this shouldn't be that much of a surprise to you. The block doesn't continue to slide along the table because of friction, because friction, an external force, constantly acts on the object. And that's an important thing to note. Now, as it turns out, friction's pretty complicated, but we can make an attempt here to come up with some broad definitions of friction, broad definitions of friction in physics. That's what I meant to say. And so even here, when we try to come up with this broad definition, we have to be a little careful. And so basically what we're going to do in this unit is we're going to go through and we're going to kind of constantly refine what it is that we're saying to make it clearer and clearer and clearer. So the first thing we're going to ask here in the question, how do we describe friction? We're going to say friction is a force that limits the motion of an object. That's not exactly true. Sometimes friction makes objects move. But at least for right now, we're just going to say friction is a force that limits the motion of the object. We'll get to the cases when friction makes objects move in a little bit. But for right now, we can say that friction is a force that limits the motion of an object. And so the obvious question here to ask is, well, like, how does that work? How can we describe the effects that friction has if it is indeed a force? What do forces make objects do? You see it when you see friction in action. Since friction is a force, it can cause objects to accelerate. And we could just go ahead and get rid of that last part. Since friction is a force, it can cause objects to accelerate. And that's true because objects accelerate when they're subject to a force. Sorry, my MacBook is still broken. I can't edit that out, so just pretend that wasn't there. Since friction is a force, it can cause objects to accelerate. And the last question before we move on. How can we describe the direction in which the friction force acts on a moving object? Well, this I'm sure you remember from honors physics. Since friction acts in the direction opposite of motion when it's acting on a moving object, it makes objects decelerate or slow down. And so when an object is in motion, the force of friction always acts opposite the direction of motion. That's an important thing to remember. Obviously, we're going to continue to bring that up. Okay, so the first thing that we should really get into here is like what we know about friction. And what we know about friction, we've actually known for a long time. Scientists in like the 14, 15, 16, 1700s did a lot of experiments where they came up with basically some experimental observations about how friction works. And so what we're going to talk about here are just some experimental observations about friction. I actually, when I was in college, did a series of experiments because they made me in freshman physics, actually confirming all of these. So if you were to perform experiments, it's important to realize you could see this with your own eyes. Now, as it turns out, because we have limited time in this course before the AP test, we don't actually do this experiment before the AP test, but we do sometimes in years past go back and take a look at these experiments after the test. And, you know, if we happen to end up going back to school full time this year, then we may have the opportunity to do that. The first experimental observation about friction is called Amundsen's first law. Amundsen was the scientist who discovered this, obviously. And Amundsen's first law said the force of friction is directly proportional to the applied load on the surface. Now, we can refine that a little bit, right? Because the applied load on the surface, according to Newton's third law, is equal to the force the surface applies on the object. And so, in other words, to put this in terms that we can easily understand, the force of friction is directly proportional to the normal force, is essentially what Amundsen's first law is saying. And so I'm going to write over here the force of friction, which is an F with the subscript F, usually like the italics fancy F there. It's directly proportional to Fn, the normal force. That's Amundsen's first law. Amundsen's second law is the next experimental observation of friction, and Amundsen's second law says the force of friction is independent of the area of contact. That's pretty weird, I think, because that's a little counterintuitive. Like, let's say we have a surface and we have like a really rectangular block that has a very long length, but it's not that wide. And so it looks like that. Essentially, what Amundsen's second law is saying is that if you put the block like that, or you put the block like this, the force of friction is going to be the same. It's independent of the area of contact. Of course, a good question is, well, why is that true? Why does that make sense? And the answer here is pretty simple. It's because actually, let's put it this way first. The first thing that we can say that it's pretty simple is that the friction force is directly proportional to the normal force. And so the reason why the friction force is independent of the area of contact is because in both of these cases, Fn equals Fg. And so the normal force is the same in both of these cases. But like, if you really want to dig into it and say like, well, there's more surface exposed when it's laying horizontally like this and not up vertically like this, like, why does that really make sense? And there's actually a pretty good reason. The reason is when you lay the object down like this, as it turns out, the surface area exposed to the table or surface or whatever this is large. And that actually means that the pressure exerted on the surface is actually pretty small. And when the block is vertical like this, since it's putting all of its weight on a much smaller area, since that weight is not well distributed over a large area, there's actually more pressure. And so those two things sort of cancel each other out, right? It's a lot of surface area in this case, but it's not that much pressure. And it's a little bit of surface area in this case, really not that much, but it's a lot of pressure. And so both of those things end up basically reducing to nothing. The force of friction doesn't depend on the area of contact. Now, as it turns out, pressure's got nothing to do with it, but that's an easy way to understand it, is that it only depends on the normal force. And the reason why it only depends on the normal force is because, when you expose more area, you might think there's more friction, but there's less pressure. And the last observation about friction, even though we didn't actually formally introduce this yet, but we'll get to it. As I'm sure you remember in honors physics, there's a kind of friction called kinetic friction. The word kinetic always refers to motion, right? So Coulomb's law of friction, yes, that Coulomb of Coulomb's law fame, but that's the static electricity equation. This is a different Coulomb's law. That's why it's called Coulomb's law of friction. Says that kinetic friction is not dependent on the velocity of the object. No matter how fast it's moving, it does not depend on the velocity of the object. I think that makes sense. I don't always understand why it is that people get confused about this. I think it must be because, when the object is moving really fast, the surface of the object is like rubbing over more of the surface of the table or something, I guess. And you might think that means there's more friction, but it doesn't work like that. Kinetic friction has no dependence on the velocity of the object, and that is just the way it is. And now that we've said really a bunch of stuff about what we know, we now want to really get into why it's true, how we know it. And we can only go so far. So the first question we can ask here is well, why does friction exist? And we can say, well, friction exists because of contact between surfaces. Smooth surfaces on a microscopic level are really rough. So like if you look at a really smooth thing, even like a knife seems really smooth. It's actually really jagged if you look at it on a microscopic level. The important thing to say, though, and I cannot overstate this, on a fundamental level, we have absolutely no idea what friction is or why it exists. Not a clue. As it turns out, it's pretty complicated. We thought we had a pretty good handle on friction before quantum mechanics and atomic physics. And then as soon as we figured out exactly what atoms are and the mysterious ways in which they work, we were like, oh, wow, there's a lot that we don't understand about this. And so current theories propose a sort of electrical attraction between atoms that cause the objects to like sort of stick together a little bit, but we really can't say for sure. And so it's important to realize, though, I like this because like this is what science is. Science is all about like, okay, even if we can't figure out why this is true, we can sort of just take like a totally dispassionate look at this and say, like, how does this work? Let's figure it out. Let's sort of make a model in our head and then let's test that model. And if our model assumes, hey, this thing should happen and it happens, then that gives us a pretty good indication that we're onto something. And if we say, if this thing is true, then this should happen, and it doesn't happen, then we know it's wrong. That's how science works. We're constantly refining and testing and changing and refining and testing and changing until we settle on something that stands up to real scrutiny. And that's a major point. Now, there were a lot of things in those last few slides, and we are going to move on to say a lot more stuff. So if you didn't get a chance to finish writing some of those things down, I suggest you pause the video here and go back and make sure you write those things down, because it is very important to know the basics about friction that we've discussed so far, those experimental observations of friction, and really why friction exists. So take a second to pause this video here and make sure you have all that stuff written down, and then we'll move on. Okay, so just to sort of get a good visualization for what we just said here, that friction exists because of contact between surfaces, and that smooth surfaces on a microscopic level are rough, here's a nice little visualization of that. So like if we sanded a wooden crate, I'm sure you all have some experience with this because you like do a little bit of like wood working in shop. If you sanded a piece of wood, like you can get it to feel super smooth. But if you actually zoom in on it, like with a really fancy microscope, you'd actually see that it has like jagged edges and like these little teeth, sort of. And so our basic description for now is going to be that all of these seemingly smooth objects on a microscopic level have these sort of jagged teeth, as is shown here in this zoomed in image, that just get like stuck on each other. And the fact that these things get stuck on each other is what gives rise to the force of friction that we see on the macroscopic scale. Okay, so now we're really going to get into some detail. The first thing we should say is that there's a bunch of different types of friction. And this really begins the time of the year where we say, hey, remember that thing we said in honors physics? Yeah, it turns out that was a lie. And so in honors physics, we said there are two types of friction. That's a lie. I might have introduced the multiple types of friction in my class. I'm not sure if Miss Neron does, frankly. But if you have in your head there are two types of friction, there are not. There are many. And so we can say here there are many different types of friction forces that act on an object depending on exactly how the object is moving. The first kind is called static friction. That we covered in the honors class and will cover here. The second type is kinetic friction. That we also covered in the honors physics class and will cover here. The third type is fluid friction, which I'm sure makes all of you think of like a ball moving through water or something, but it's important to realize air resistance is also a type of fluid friction, because air scientifically speaking, is a fluid. And that probably sounds pretty weird, but essentially we just say that air is a fluid like water, but just with a really, really, really small density. Other than that, though, it behaves exactly like a fluid. It's kind of sketchy, but you get the idea. It certainly isn't a solid, and I hope that much we could all agree on. And then the last kind is called rolling friction. Now, this is the part that's weird, and so I want to make a note about it. There is actually a thing called rolling friction. There's an equation for rolling friction. There are numbers that you want to use for rolling friction. But for this course, when an object is rolling, we're just going to say static friction is what's acting on the object. And so for kinetic friction, we always say kinetic friction acts on an object when it's moving, but I think we should be pretty careful about that. Kinetic friction really acts on an object when it's sliding. If it's rolling, really rolling friction acts on it, but in this course, we basically just say that static friction is what acts on it. Honestly, I don't really know why they do this. I think they just, if you really want to be highly precise about everything we talk about in this course, it would take us like 5 years to cover. And so we don't do that. We just say they're static and kinetic. Take a second to pause this video here and write that down. And when you hit play, we're going to start off with static friction. Okay, so there's a lot that needs to be said about static friction. And the first thing we're going to say here, is a basic description of static friction. How can we describe static friction? Static friction is a friction force, which is a contact force. Remember, static friction only acts when the objects are in contact. And static friction is a friction force that acts between two objects when there is no motion. That's why it gets the name static friction. And so it only acts when the objects are at rest. And so I'm going to write that here. Only acts when objects are at rest. And that's an important point. Now, of course, we can ask the question, well, how do we actually know that static friction exists? Like, how do we know that if an object is just sitting there, that there is a friction force acting on it at all? And, well, we can say something pretty simple here. If the question is, how do we know the static friction force exists? We can say we know the static friction force exists because when you apply a small force to like a super heavy object like a refrigerator, it doesn't accelerate. On a frictionless surface, if you applied the tiniest little force to a super heavy object like a refrigerator, it would start to move. Now, according to Newton's second law, it would move really, 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 really slowly, but it would move. And so we know that because when you pull on something really, really heavy, it doesn't move right away. We know that there must be a static friction force, which is counteracting the applied force. That's very important. Now, the other thing to say about static friction is, well, lie alert. There's a lot of lying that goes on about static friction in New York State physics regents courses all across New York because static friction is complicated. And so this is a big note, write this down. The most confusing thing about the static friction force is that the static friction force can change its magnitude. Now, I go into this a little bit in my course because I try in the honors physics course to lie to you as little as possible, although obviously it just needs to be done to finish all the stuff before we get to the regents. But the most confusing thing about the static friction force is that it can change. Now, exactly how it changes We're not really sure. This goes back to that whole thing of like, we have no idea what friction is or how it works. But we can at least definitely say, like, for sure, that the static friction force changes its magnitude. How do we know that the static friction force changes? That's a good question. You could do an experiment, but you could really just think about it. And so we can say here that we know the static friction force changes because certain objects will not move when larger and larger forces are applied to them. And so what we're saying here is, as a result, the static friction force ends up having a maximum. The static friction force will continue to counter the applied force until the maximum is reached. And once the applied force exceeds the maximum friction force, the object will move, and then kinetic friction sets in. Now, don't get me wrong. This is insanely confusing, but we are going to take it piece by piece. So I'd like you to pause this video here and write that down. And when you hit play, we're really going to try to get into that. Okay, so if you look in your AP physics reference table, they have an equation for the force of friction. And it looks like this. And I'm sure looking at that, you are probably thinking, ooh, what is that? Now, despite the fact that this is what it says in the reference table, I don't really want to use this that much. I'm probably almost never going to write this down. Having said that, I think on the AP test, if you are citing this equation, you should write it that way. But for my tests and like on homeworks and stuff, I want you to use it a little bit differently. The first thing that we should say is this equation has absolute value bars because it only deals with magnitudes, right? Because like if we're talking about a surface, it's a little weird because the normal force is going to act perpendicular to the surface and the friction force is going to act either left or right. And I just put left in this case. It doesn't really matter though for the purposes of this discussion, but those are at right angles. And that's a little weird. And so because it's like really sketchy to just say, we're going to take this normal force, which acts perpendicular to the surface, and we're just going to multiply it by a number, and then all of a sudden the direction is going to be totally different, doesn't really make sense. So this equation deals with magnitudes only. I want you to write this equation down, though, and then I want you to write next to it magnitudes of FF, the force of friction, and Fn, the normal force, only. Definitely pretty important. And what I want to talk about next is our version of it, the version of it that we are going to use when we're solving problems and when we're talking about these things. And so our version is going to look a little something like this. We're actually going to have two different versions of this. The first version is we're just going to say the force of static friction, which I'm actually going to add a subscript S on. Why do I want you to add a subscript S on this? It's to differentiate it between the static friction force and the kinetic friction force, right? And I'm going to say that the static friction force is less than or equal to the coefficient of static friction, which is what that mu symbol means. And I'm going to actually fix that because that was a little sloppy. Remember, that's the mu from the metric system. It's a Greek letter. And so if you just sort of draw it like it's shown there in the reference table, it has two tails, sort of looks like a U. Let's not go nuts. The coefficient of static friction, and then that's times the normal force. And so there's our first equation of our version that we're going to use. And so essentially what this equation is saying is the static friction force can change its magnitude. But that it will always be less than or equal to whatever the product of this term, the coefficient of static friction, and the normal force actually is. So let's actually label those terms here. Mu with the subscript s is called the coefficient of static friction. And the thing to know about the coefficient of static friction is that it's a unitless number. It's literally just a number. It has no units. F with the subscript n here is the normal force. And of course, the normal force is measured in units of newtons. And then F with the subscript s is the static friction force. And that, of course, is measured in newtons. And now here, obviously, the big question is, well, why did I write number 1 and not number 2? And the reason why I wrote number 1 and why I'm about to write number 2 is that there's actually a second, arguably more useful version of this equation that we need to use. And it all goes back to what we just said before. Let me just go back to that. The static friction force can change its magnitude, but what's really important about it is that it has a maximum. And notice, we can actually tell it has a maximum from this equation and our version of the equation. We can tell it has a maximum because it says the static friction force is always going to be greater than or equal to the coefficient times the normal force. And so the next equation we're going to write is F with the subscripts F, S, and then we're going to write max. Because what you'll see when we are like analyzing situations and doing problems is that it's less important to be able to say like, well, the force is going to be less than or equal to this number. It's actually really important to just know what is the maximum value the static friction force can be. And so the static friction force maximum is equal to the coefficient of static friction times the normal force. And so we'll go ahead and add that to our list. F with the subscript F, S, and then max is the maximum static friction force. And that also is measured in newtons. Now, one thing we definitely want to note here before we move on is most of the time you use this equation, you're not actually going to use that version of the equation. And I know that sounds weird because didn't you already say there's 2 versions? Well, this is the same version, but it's important to realize, and I'm just going to write this over here, on a flat horizontal surface, now that you've heard me say flat and horizontal, I hope you know what I'm talking about. On a flat horizontal surface, there's a thing you're supposed to know about the normal force already. And the thing you're supposed to know about the normal force already is that on a flat horizontal surface, the normal force is equal to the object's weight. And so on a flat horizontal surface, which is what we're almost always going to see, is that the static friction force maximum is equal to the coefficient times m times g. And because we're almost always going to be given the mass of the object in kilograms and not its weight in newtons, that's the version of the equation that we want to use and think about. And so just to totally wrap this up here, I'm going to come over here and I'm going to write m, of course, is the mass measured in kilograms. And the g, of course, I'm not even going to write the whole word. Gravitational acceleration, the 2 words, I'm just going to write 9.8 meters per second squared. You should know what that is by now. And that's that. Now, one thing I want to say, and if you want to write this down, that's up to you, but I feel like it wasn't addressed and that would be silly to move on and not address this. One thing that we should definitely say, because this used to confuse the heck out of me when I was in high school. Like, there's a pretty good question that we can ask. And that question is like, well, what is the coefficient of friction? And oftentimes the answer that I would get in high school or even in the beginning of college is, well, the coefficient of friction is a unitless number. And you're not really telling me what it is. You're just telling me things about it. And so maybe we should refine the question a little more. We can say, what is the coefficient of static friction? Or more pointedly, what does it mean? That's an interesting little question. And you can really tell what the coefficient of static friction means if you take the equation that we just developed for the maximum static friction force and you solve it for the coefficient. And what you see when you take this equation and you solve it for the coefficient is, well, you see exactly what the static coefficient is. The coefficient of friction is the ratio of the force of friction to the normal force. Let's actually just write that up here. The coefficient of friction, that's a very poorly written mu, but that's a mu nonetheless. The coefficient of friction is the ratio of the force of friction to the normal force. And that's it. So, and this was posted online for you on Google Classroom today, and it should be in the classwork section as well. What you should see on the Google Classroom page is that I've now put up a series of charts from all of the different textbooks that make up our packets with various different readings for the coefficient of friction. Now, why did I specifically label the textbooks? Well, I labeled the textbooks because if you are doing work from pages 1 through 9 of the packet, these are the coefficients of friction they're expecting you to use. And so just to be totally clear about the point that I just made, I just want to zoom in on this section of the chart here. And let's just say, when you look at a chart and the coefficient of static friction for, let's say, wood on wood is 0.4, essentially what that means is when wood is in contact with wood, and obviously that's like too vague because like the wood could be sanded, it could be a different kind of wood, but whatever. When the textbook says it's a wood block on a wood table, don't go too nuts about the specifics. When the textbook says it's a wood block on a wood table, what the coefficient of friction being 0.4 means is that the friction force supplied by the wooden table is 40% of the normal force supplied by the wooden table. That's it. So when you have homework problems and you see that the textbook says objects, like lists objects, it's a rubber whatever on a wet concrete whatever, you just use that number in the sheet in that chart. Okay, so now that we've wrapped up the discussion of the equation of the static friction force, we are going to solve a problem, but not for another couple minutes because we got some questions to ask. The first question we have to ask here and really get into is about the maximum static friction force. And so let's just be totally clear. There exists a value called the maximum static friction force, which represents A, the largest possible amount of static friction that can act on the object, and B, the minimum force that needs to be applied to make the object move. It's both. And the way that that works is pretty confusing. Because what happens is pretty confusing. And so let's just write down these three things and then we'll take a look at how that works. The first thing we'll say here is that when the applied force, when the force you apply is greater or equal to the maximum static friction force, the object will begin to move and the friction force will change from static friction to kinetic friction. What we can also say here is that when the applied force is less than the maximum static friction force, the static friction force will change its value so that it's always equal to the value of the applied force. This ensures that the net force is 0, which really makes sense because the object doesn't move. And lastly, we'll say when a force is applied, it must be larger than that static friction force maximum in order for the object to move. And when the applied force reaches the magnitude of the static friction force maximum, the friction force changes to the force of kinetic friction, which notice is written in the same style as the force of static friction, F with the subscripts F and K, and then stays at that value. Let's be clear. This is confusing. But now, hopefully, after you write that down, we'll be able to take a look at a visual representation of this, like a thing on a graph, and hopefully it'll make a little more sense. So take a second to pause this video here and write that down, and when you hit play, we'll move on. Okay, so there is a very important kind of graph that we need to look at in this class, and it's called a drag test graph. What a drag test is what you get, basically, when you take an object on a surface, you tie a string to it, and attached to that string, you have a force sensor. And when you very lightly pull on that object, and then you pull more and more and more and more and more and more and more until the object starts to move, you are performing what is called a drag test. And when you do a drag test, you get a graph that looks like this. I do not want you to very meticulously draw this graph, but take a second to pause this video here and make a quick sketch. Just label these values on the x-axis and y-axis very, 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 very quickly. And notice on the y-axis, it's the force of friction that is being plotted. And on the x-axis, it's the applied force, which, just to be totally clear, is also measured in newtons. Take a second to pause this video and draw this graph. And when you hit play, we'll talk about it. Okay, so the first thing that we should say here is that let's say you did a calculation using the equation FFS max, the static friction force maximum, is equal to the coefficient times the normal force, and you got 75 newtons. That's what this number is showing. This part of the graph is showing. The static friction force maximum is 75 newtons. So how are we supposed to understand this graph? Well, what we are saying is that when you apply 25 newtons, since the static friction force maximum is 75, that's not enough to make the object move. So the friction force will be 25 newtons, notice, which is equal, because the net force is going to be 0 because the object is not moving. Well, what if you apply 50 newtons of force? Well, it's not enough to make the object move, so the force of friction will be 50 newtons, canceling out the applied force and making sure the object doesn't move. What if you apply 74.9 newtons of force? Well, that's not enough, so the ground will apply a 74.9 Newton friction force in the object and will make it move. And now we obviously get to the big question here, which is what happens when you apply 75 newtons? Well, when you apply 75 newtons, something happens. The object begins to move. And what actually happens is all of a sudden the friction force drops down from the static friction force maximum to the kinetic force of friction value. How exactly does that work? We have no idea. But we do know that once the static friction force maximum is reached, the object will begin to move. And what we can say for sure is that something about reaching that 75 Newton force does something probably to the bonds, the atomic bonds that are experienced there between the surface and the object, and causes the thing to move. It's weird. Now, let's be clear about something. the friction force dropping is what makes the object move. A lot of people misinterpret that and think it's the other way around, that it's now that the object is moving, the kinetic friction force begins to act. It's not how it works. This also addresses an important confusion because a lot of people think, well, wait a second, if the static friction force, let's just say you're trying to pull the object to the left, if the static friction force is 75 newtons and you apply 75 newtons, don't those two forces just cancel each other out and the object won't move? It's a good thing to think about. But what weirdly happens when you apply 75 newtons is that, boom, all of a sudden the friction force drops down to 50 newtons, and now clearly you can see there's a net force to the left, and the object will begin to move. It's really weird. But that's what happens. It's a little bizarre. And so as we said, when the applied force is greater than or equal to the maximum static friction force, the object will begin to move, and the friction force changes from the static friction force to the kinetic friction force. It drops down. And that's the idea. Now, it doesn't happen like instantaneously as this graph would suggest. If we actually plot the force versus the time instead of the force versus the applied force, it actually does take a quick second. This is a real-life drag test graph. You don't have to draw this or anything. And I'll actually, when I get back to school next Tuesday, I will show you like an actual version of this so you can see how it works in real life. And what you see is that you pull and you pull and you pull, and the object doesn't move, and the force meter reading goes up and up and up, and then boom, all of a sudden it drops down. And the instant you see it to drop down, the object starts to move. It's weird. And what you see there is that the peak level is the force of static friction, maximum. And this level here, which they're showing you is this green line, that's the force of kinetic friction. Speaking of force of kinetic friction, let's talk about the force of kinetic friction. In the reference table, the equation for the force of kinetic friction looks like this. That gives us no help. So we'll come up with our own version, and there's really only going to be one thing here. We're just going to say that the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force, where mu k is the coefficient of kinetic friction, which is a different number. You can also see those in that chart. F with the subscript n is the normal force. And F with the subscripts F and K are the force of kinetic friction. And both of those are measured in newtons, whereas the coefficient is unitless. Also, just before we move on a flat horizontal surface, it should be noted we can make the same modification to the kinetic friction force equation that we made to the static friction force equation, which is that the coefficient of kinetic friction will be equal, or excuse me, the force of kinetic friction will be equal to the coefficient of kinetic friction times m times g. What you use, of course, depends on what you're given. Now, the last thing I want to do here is take a second to discuss real fast what we just said about the kinetic friction force in relation to the static friction force. Because what we said about the kinetic friction force in relation to the static friction force is that the kinetic friction force is lower than the static friction force. And we would like to figure out like why that's the case. So the question here says, how can we use Newton's laws to explain why the force of static friction is always larger than the kinetic friction force? And it actually makes sense. The static friction force is always larger than the kinetic friction force because it's always harder to start an object in motion than it is, I should say than it is to keep it in motion. As according to Newton's first law, an object always has a tendency to maintain its state of motion. Take a second to pause this video here and write that down, and when you hit play, we'll take a look at a problem and wrap it up for today. Okay, so before we move on, I just want to be clear that was supposed to say it's. It is always harder to start an object in motion than it is to keep it in motion. Well, I guess I'll just get rid of that now. And so that's the idea. We can sort of rationalize that with the first law. That an object has a tendency to maintain its state of motion. And when it's at rest, that thing wants to stay at rest. And you got to give it a lot of force to get it to go. Once it is moving, though, it wants to move. And so it's easier to keep it in motion. Okay. Now, the last thing we're going to do for today, because this video is already getting a little long, is I'd like to just go ahead and solve a problem so we can see how these forces work, how the equations work, and how we can calculate these things. So this problem here says a 10-kilogram box rests on a horizontal floor. The coefficient of static friction, mu with the subscript s, is 0.40, and the coefficient of kinetic friction is mu with the subscript k is 0.30. It says determine the force of friction if the applied force, F applied, is 0 newtons, 10 newtons, 20 newtons, 38 newtons, or 40 newtons. And so based on everything we said so far today, it should be clear to all of you that in order to figure out if the object moves, we have to know what the static friction force maximum is. And since we're going to calculate the static friction force maximum, we might as well calculate the force of kinetic friction just so we can see how this thing works. So let's go ahead and solve for both of those forces. And so we'll make our list of knowns here. Mu with the subscript s, the coefficient of static friction, was 0.40. The coefficient of kinetic friction is 0.30. The mass of the object was 10 kilograms. G, of course, we'll write down because they told us it was on a horizontal floor, is 9.8 meters per second squared. And we are going to want to find the static friction force maximum and the kinetic friction force. And we have everything we need to solve for both of those. And so the first thing we'll do is we'll write down the static friction force maximum is equal to the coefficient times the normal force. That's the equation. But of course, that's not the version we want to use. We want to use the version that says the static friction force maximum is the coefficient of static friction times m times g. And so to round this one off here, we'll hit FFS max is equal to the static friction coefficient 0.40 times m, 10 kilograms, times g, 9.8 meters per second squared. And when you do that math and you multiply all those numbers, you get that the static friction force maximum is equal to 39.2 newtons, which we'll round to two significant figures since everything in the problem is to two significant figures, and we'll call that 39 newtons. Now, that's actually enough to answer like a lot of this question, but we'll go ahead and, just to be totally clear, we'll just go ahead and solve for the kinetic friction force also, and we'll say that the kinetic friction force equation, as we just gave, is the coefficient of kinetic friction times the normal force, which is in fact equal to the coefficient times m times g. And so now instead of taking 0.4 times 10 times 9.8, we'll take 0.30, because that's the coefficient of kinetic friction, times 10 kilograms times 9.8 meters per second squared. And when you do that math, of course, we want to keep this to two significant figures. When you do the math, you get 29.4 newtons. And that, to two significant figures, is 29 newtons. Pretty good. And now we definitely have enough to be able to answer big pieces of this question. And just to make this a little quicker for all of us, I'm actually going to go ahead and type the answers to these just so we can have it all down. And so I'm going to get ready for that. Okay. All right. So the first part of this says, determine the force of friction if the applied force is 0 newtons. Well, if the applied force is 0 newtons and this calculation tells us the static friction force maximum is 39 newtons, then that means it takes 39 newtons to make the box move. So that means the box isn't going to move. So for part A, we'll say the box won't move. So the applied force is canceled by the static friction force maximum, which in this case is 0 newtons. If you don't apply a force, there's no static friction force that to cancel anything out, really, because the thing is not moving. The net force has got to be 0. You got 0 applied force, you got 0 static friction force. For part B, it says the applied force is 10 newtons. Well, the box won't move, so the applied force is canceled by the static friction force maximum, which in this case is going to be 10 newtons. They have to cancel, so the net force is 0. And the acceleration is 0. And notice here, that's going to be the answer for part C and for part D, because those applied forces are not enough to make the object move. Then the static friction force is going to cancel out the applied force to keep the net force at 0 so that the acceleration is 0. That's the idea. So we'll put this in here twice for C and D, and we'll say in this case for C, the applied force was 20, so the static friction force maximum will be 20. And then even when it gets all the way up to 38, because the fact that the static friction force maximum calculation tells us the maximum value of the static friction force is going to be 39 newtons, and the minimum force you have to apply to make the box move is 39 newtons, then 38 newtons is not enough. They got to cancel, so the net force is 0 and the acceleration is 0. Now, the last applied force given, 40 newtons, is larger than the static friction force maximum. So for E, we'll say the applied force is larger than the static friction force maximum, so the object will move. The friction force will be the kinetic friction force, which has a value of 29 newtons, which we calculated. So the pattern here, the scheme here is pretty simple. When the applied force is less than the static friction force maximum, it's not going to move. Whatever this actual static friction force is, it's got to be equal and opposite of the applied force, so they cancel to keep the F net 0 to keep the acceleration 0. But if the applied force is larger than the static friction force maximum, then that's going to make this thing move. And so the friction force that's going to be acting on it is the kinetic friction force. And it has a value of whatever the equation tells you. And when we did that calculation, we got 29 newtons, so it's going to be 29 newtons. Notice, though, the question also asked, if the box moves, then what's the acceleration of the box? And so we have to figure out what that is. And I think at the end of the day, this last thing that we're going to do here, because I hope it really drives the point home, is that at the end of the day, this is a forces problem. So if we're thinking about this box on the flat horizontal surface, we got a normal force. We got a weight. we have a friction force. And notice here, because the friction force is a small number, the coefficient is less than 1. If you saw it in that chart, because we have a small number times the normal force, the friction force is going to be smaller than the normal force. And then we have an applied force. Let's just say the object is being pulled to the left. Now, in this case, the applied force should be smaller than the force of gravity if the thing is 10 kilograms. So let's just make sure we're being totally precise about that. The scale here is a little sketchy, but you get the idea. Make that a little longer than the friction force. We'll make these guys a little bit longer, but that's the idea. And so it's good to do these free body diagrams with a pencil so you always have them straight. Now, of course, the normal force and the gravitational force cancel each other out, but if the acceleration of the box is going to be to the left, then we'll say here that we take ma and we set it equal to the force in the direction of the acceleration, the applied force, minus the force going in the opposite direction, the force of friction. It's a free body diagram problem. And then all you got to do here to solve for the acceleration is divide by the mass. So we have the applied force minus the force of friction over the mass. And this is a simple calculation here. The acceleration is going to be equal to the applied force, which was 40 newtons, minus the force of kinetic friction, which is 29 newtons, over the mass, which is 10 kilograms. 40 minus 29 is 11, and 11 over 10 is just going to be 1.1 meters per second squared. And that's it. And with that, that's it for today. This video is already getting to be a little bit long, and we've covered, I think, the basics of static friction and kinetic friction, and so that seems like a good place to leave off. So for tomorrow, to finish us out for the week, we'll start to talk about some of these more complicated applications of the friction force and how we can use it to solve some more complicated problems. All right, everybody. Have a good one.